Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we are going to talk about the element Einsteinium. What you see here is an invisibly small sample of Einsteinium we'll talk more about in a bit. Also, at the end of this presentation, I'll have a question for you about the future of this video series. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Einsteinium is the 99th element in the periodic table. Its atomic number is 99 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Like all the elements in this part of the periodic table, we don't have to go back in history very far for the discovery of Einsteinium, only back to post-World War II research performed at the University of California, Berkeley. Albert Ghiorso discovered Einsteinium along with Gregory Chopin, Stanley Thompson, and Bernard Harvey in 1952, but because of Cold War secrecy, their discovery was not revealed until 1955, 3 years later. Albert Ghiorso was involved in the discovery of 12 elements, more elements than anyone else. He should have had an element named after him. Unfortunately, that's not the case. Yet. The details of the discovery of Einsteinium were interesting and spectacular, to say the least. Einsteinium was discovered in the debris of the first thermonuclear explosion, a hydrogen bomb called Ivy Mike. On November 1st, 1952, the largest human-made explosion ever produced took place. Eager to discover what products were created in the nuclear detonation, aircraft were actually flown through the stem of the mushroom cloud of the Ivy Mike test. They collected particles, which were then analyzed to find which isotopes were created. Colonel Virgil Maroney led the 4 planes on that mission. One of the 4 pilots, Jimmy Robinson, died in the attempt. Brave men. The detonation of Ivy Mike took place on a tiny Pacific atoll, which you may have heard of, Eniwetok. A total of 43 nuclear tests were conducted on Eniwetok Atoll. That was between 1948 and 1958. Here is the crater left behind by Ivy Mike. It's almost a mile across. Again, Einsteinium was discovered in the debris of the first hydrogen bomb explosion. To make a hydrogen bomb, a fusion bomb, you start with a uranium or plutonium fission bomb, which initiates the fusion of hydrogen. So there are lots of fission products which are then bombarded by the copious neutrons from the fusion reaction, creating those heavier elements. More on that in a bit. Many videos of various nuclear tests can be found on the Atomic Test channel on YouTube, a frightening, if not fascinating, channel. Einsteinium was, of course, named after Albert Einstein, the most famous physicist of the day. The discoverers thought it was appropriate to give Einstein credit since his work made the creation of the element and the bomb possible. It's much more efficient to produce Einsteinium in a reactor, though the process is a bit different. We'll talk about that. Here you see the high-flux isotope reactor at the Oak Ridge National Lab in Tennessee, which began operation in 1966. Oak Ridge has produced up to 3 milligram samples of Einsteinium, requiring 4 years of production time, though more recently they produce about a microgram per year. Isotopes produced in the high-flux isotope reactor are separated here in the Radiochemical Engineering Development Center, or REDC. Handling of these dangerous materials is done in a hot cell. Here you see 9 of these hot cells. Scientists are protected by thick layers of lead glass and control the processing with robotic remote manipulators. I'm sure you've seen many of these in science fiction films. It's not fiction, though they are sometimes called Waldos from a short story by Robert Heinlein in the August 1942 edition of Astounding Science Fiction. Here he was writing under the pen name Anson MacDonald. The only other place you'll find Einsteinium is at the Research Institute of Atomic Reactors in Dmitrovgrad, Russia, the equivalent of our Oak Ridge high-flux nuclear reactor. Both reactors were designed to produce copious amounts of neutrons, useful in the production of many isotopes. These reactors are not designed to generate power. We'll need all those neutrons, but we'll take a look at that. We start with uranium-238 in the high-flux reactor. With its half-life of 4.5 billion years, we don't have to worry about this decaying away. Some uranium atoms eventually absorb 15 neutrons, and they then emit 6 beta particles to become californium-253. I'm not detailing the intermediate isotopes here for brevity. The californium-253, with a half-life of only 17.81 days, also emits a beta particle to become Einsteinium-253, with a half-life of only 20.47 days. Any refining after this must be done quickly because of that short half-life. Here you see a quartz vial containing a huge 300 microgram sample of Einsteinium-253. The blue glow is a result of intense radiation from its alpha decays, ionizing air surrounding the sample. If you had only 1 gram of this isotope, over 3,000 times the amount you see here, it would be generating 1,000 watts of heat. Einsteinium is a member of the actinide series of elements down at the bottom of the table. It's the 11th element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides and their isotopes are radioactive. Let's look at isotopes. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 99 protons for Einsteinium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 18 known isotopes of Einsteinium. And as I mentioned in the previous slide, we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of Einsteinium are radioactive. We don't really find Einsteinium in nature because of that. The word isotope comes from the Greek, isos meaning same or equal, and topos meaning place. You've used a topographic map to find your place, I assume? All these various isotopes of Einsteinium occupy the same place in the periodic table. Of the isotopes of Einsteinium, these are the longest lived, the ones with half-lives over 1 hour. I'll talk more about half-life in a bit. The longest Einsteinium half-life is Einsteinium-252, with a half-life of only 471.7 days. That's why it's not found in nature. All the Einsteinium has decayed away. It has to be manufactured, as we've seen. Before we look at the decay series of Einsteinium, let's look at radioactive decay modes. Radioactive elements are unstable and decay into other daughter products. There are 3 main ways nuclei can decay, and I'm oversimplifying this a bit. First, the nucleus can decay by giving off an alpha particle. An alpha particle is simply a helium nucleus stripped of its electrons. It consists of 2 protons and 2 neutrons. Emitting an alpha particle changes the atom to the element 2 spaces previous in the periodic table, since it loses 2 protons. Next is the beta particle. Here, a neutrally charged neutron in the nucleus becomes a proton and an electron. Added together, they still have 0 charge, like the original neutron. While the proton remains in the nucleus, the negative electron is spit out as a beta particle. Because the nucleus gains a proton in this interaction, the atom becomes the element 1 up in the periodic table. Lastly, and loosely explained, during some decay events, the nucleus can be left in an excited state. When the nucleus rearranges itself to a lower energy state, it can emit a gamma ray, an extremely high energy and penetrating photon. Here, the atom does not transmute into another element. Now, let's briefly look at the decay series of Einsteinium. It's complicated, so we won't go into detail. We'll start with the longest-lived isotope, Einsteinium-252, with a half-life of only 471.7 days. More on half-life in the next slide. As just illustrated in the previous slide, isotopes can decay in different ways. Our first decay is by alpha particle to berkelium-248, or, as I've been corrected, berkelium-248. This is the most likely way Einsteinium-252 decays. The berkelium has a half-life of 9.5 years. After a series of complicated decays, which can happen in many different ways, we eventually arrive at stable, non-radioactive lead-206 or lead-208. If you want a detailed look at this Einsteinium decay series, take a look at Theodore Gray's periodictable.com website here. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any radioactive isotope. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait 1 half-life, 1/2 of your isotope will decay, and we'll have 512 atoms left. If we wait 1 more half-life, half of that remaining half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's 1 remaining atom after 10 half-lives here. If we waited 1 more half-life, our remaining atom would have a 50-50 chance of decaying in that time. We can talk a bit about a few physical properties of Einsteinium, but not a lot is really known about this rare element. As you can see, most of the properties have an Na not available next to them. Still, there are a few things we do know about Einsteinium. Einsteinium has a density of 8.84 grams per cubic centimeter. It's a fairly dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds for comparison. You can see Einsteinium's density is comfortably between iron at 7.89 grams per cubic centimeter and bismuth at 9.78 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, Einsteinium's density is 8.84 grams per cubic centimeter, close to the middle of the chart, around the 35th densest element. Einsteinium has a melting temperature of 1,133 degrees Celsius or 2,071 degrees Fahrenheit. That's around the 43rd highest melting point, about the middle of our chart, around the melting temperature of uranium, copper, or gold. Although this figure is a bit uncertain, Einsteinium boils at 1,269 degrees Celsius or 2,316 degrees Fahrenheit, giving it around the 49th highest boiling point of all the elements, below average on this chart. That's only 136 degrees Celsius above its melting point, yielding a very small liquid temperature range. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range. As I mentioned, Einsteinium's liquid temperature range is far below average with a 136 degrees Celsius range, the lowest liquid temperature range of solid elements. The smallest liquid temperature range belongs to neon, which is liquid in only a 2.51 degrees Celsius range. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. The size of the Einsteinium atom is around 490 picometers, a diameter about 4.6 times the size of the hydrogen atom. Let me quickly mention that the 490 picometer size is not well established and is only a best guess. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are astonishingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. The size of the Einsteinium atom places it just above the size of the potassium atom, a pretty large atom if my numbers are correct. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of Einsteinium. It has the simplest spectrum we've seen so far, only 3 colors in the visible part of the spectrum, 2 closely spaced greens and a lone yellow. This is the last known spectrum of the periodic table I could find. As you can see, the rest of the elements on this chart are blank. The quantities of higher elements are insufficient, or the half-lives are too short to do the required experiments. Spectra of the elements uniquely identifies them to scientists, as each gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Surprisingly, well, not so surprisingly, there are no real-world applications for Einsteinium, and its only use is in research and the production of even heavier elements, which I guess are also research projects. This group of researchers, Leticia Arnedo-Sanchez, Catherine Shield, Corey Carter, and Jennifer Waker at the Lawrence Berkeley National Laboratory used an Einsteinium sample weighing only 233 nanograms, that's 233 billionths of a gram, to reveal some of the chemical properties of the element. Japanese researchers working with the Japan Atomic Energy Agency, or JAEA, are trying to explore the nature of the fission process using 1 microgram of Einsteinium as a target material inside that spherical chamber you see in the frame right now. They are also using powerful X-rays to investigate the chemistry of elements in the lanthanides, known as the rare earths, as well as the actinides. These are elements where electrons are added to the inner f orbital rather than to the outer electron shell. Einsteinium serves no known biological purpose, and you certainly have none of this stuff inside you. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about Einsteinium. Forged in the furnace of E equals mc squared. Ivy Mike's baby. Here, I would normally let you know what's coming up next month, but past Einsteinium, there's not much to say and not much known about elements 100 to 118. Tales from the Periodic Table started as a set of live talks at the Exploratorium, a science museum in San Francisco, and turned into recorded YouTube presentations during the COVID pandemic. This means there are no quality recorded talks for elements 7, nitrogen, through 45, rhodium. So here's my question to you. Should I continue with very short videos about elements 100 through 118, or should I loop back and recreate nitrogen through rhodium as high-quality YouTube videos? Please leave a comment below and let me know. I'm leaning towards going back and filling in the missing elements since they will probably be much more interesting. What do you think? I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element Einsteinium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And of course, I'm required by law to say this, smash that subscribe button.